Hi everyone, I'm Talia Nassi and I'm a Senior Developer Advocate here at AWS Serverless. Today we're going to talk about testing serverless applications. Basically, I build serverless things and then I teach the world about them. So before becoming a dev advocate, I was a test engineer for a few years. That's how I got involved with TechWell and the STAR conferences. So I did test engineering and QA and automation, all of that fun stuff. Today we're going to cover a few things. We're going to talk about what it means to be serverless. We're going to get into event-driven architecture, and then we're going to talk about the challenges of testing serverless applications, what the types of tests are that you should be implementing, and then we're going to end with the best practices of testing your serverless applications. So let's get started. When we say serverless, we mean it's the removal of server operations. And there are 4 tenets that define serverless as an operational model. Firstly, there is no infrastructure to provision or manage, so there's no servers to spin up, operate, or patch. There's no physical or virtual container orchestration. Serverless applications automatically scale by unit of consumption rather than by server unit. So automatic scaling is a really big win for companies because generally, you create multiple MVPs and you don't want to build all of them out for scalability. Serverless also has a pay-for-value billing model, which means you only pay for what you use, not for idle time. So if you have an idea that's not taking off, some of them can get expensive. So what this means is that you can experiment more. Let's say I have an idea for a new feature and Eric has a competing idea for a new feature. Eric and I can A/B test our features, and regardless of which feature has a higher conversion rate, it's not going to cost much because you only pay for what your customers are using. And lastly, serverless applications have built-in availability and fault tolerance, so there's no need to architect for that because it's built into the service. And this is important because things will break, unexpected things happen. There's earthquakes, spaghetti and meatballs fall from the sky. So what do you do if the servers handling your project fall over? How do you know that all of your versions are in sync with all of the regions? Have no fear, serverless is here, my friends. And so what all of this means is that you have greater agility, you have fewer operations, you can focus more on your product and your business logic and less on your infrastructure. You have a faster time to market because of this, and you have cost that grows with your business. Serverless applications are composed of 3 things. First, we have the actual Lambda function, and a Lambda function contains your business logic and can be written in one of these 6 runtimes or your own custom runtime. It's made up of code you've written to react to something that happened, and that something that happened is called an event source, and Lambda functions are triggered by an event source. An event is something that happened. So maybe a file was uploaded to S3, maybe a DynamoDB table was updated, maybe a request hit an API endpoint. So it's something that happens that triggers a Lambda function and makes it come to life. Then we have the destination, which answers the question, what do you want this Lambda function to do once it's invoked? Do you want it to talk to another service? What do you want it to do? So after the function is invoked, it's going to go and perform whatever it needs to do, update a database record, go return something to a client, go talk to another API or endpoint that exists, or maybe send its output to another service. And these services can be other AWS services or third parties that are integrated with AWS. So just to make this more clear, Lambda has event sources that exist, and we're going to cover events in a second, and it also can send function results to other services, some of which are also possible event sources. So you have event sources, and then those event sources can also act as a destination if you want that information to go back to a service. Lambda is event-driven, and to understand events and event-driven architecture, let's go through an example. The example is this website we run named after a river in Brazil, and I'm guessing a couple of you have visited this site before. The main objective of this site is to get you to click on the Place Order button. Once you place that button, a bunch of things happen. First, we check your credit card to make sure you can pay. Then we have to get the merchandise off the shelves and onto the trucks, and so on. And that all happens in an Amazon fulfillment center. There's no synchronous API call for the Amazon backend to package and ship products. What the front end does after your payment is confirmed is it puts together some information describing the event and then puts your account number, your credit card info, and what you bought in a packaged event and puts it into the cloud. Later, another piece of software will pull it off and start the packaging, shipping, and all of that. Now, the key point about this process is that all of these things can run at different rates. And normally the rate at which people click place order and the rate at which the fulfillment centers can get the boxes out of the doors are roughly equivalent. But on days like Prime Day, Black Friday, like really big sale days, people hit that button immensely faster than the fulfillment centers can operate. And that's okay. The back end will work itself through. In the standard microservice API world, you have directed commands. And API thinking is synchronous thinking. So you can't move on until the API response comes back, right? You're sending commands. So go do this thing, go create this invoice, add this product to the shopping cart. It has an intent that's directed to a target. Like we said, serverless applications are event-based, and we talked about this earlier. It comes with challenges, right? You have to handle asynchronous behaviors and external resources, and the way that an event works is like this, right? You have this thing that happened. Again, maybe a new file was created, maybe an error occurred, maybe a new customer has been created. It tells you a fact. And events are also immutable, which means they cannot be changed. And in practice, events are just a JSON object that tells you something that happened. And a lot of people get scared when they think about events and how to use them, but all it is it's an envelope with a description of what's inside, and then inside that envelope is a JSON describing what the event is and what happened. So again, with events, you're telling a fact and others decide what to do with it. So think of a coffee shop. A customer comes in and orders an espresso, and when the barista hears that, he starts making the espresso. When the pastry guy hears that, he says, oh, this isn't a pastry, I don't care about this, and he moves on with his day. But if a customer comes in and orders a chocolate croissant, then the barista says, I don't care about that, it's not coffee. And then the pastry guy says, okay, I'm going to start making the chocolate croissant. So they only respond to events that they care about. Request-driven applications that use APIs typically use directed commands to coordinate downstream functions to complete an activity, and they're often really tightly coupled. However, event-driven applications create events that are observable by other services and systems, but the event producer is unaware of which consumers are listening, and typically these are loosely coupled. At the center of event-driven compute is something called Lambda. And like we talked about before, Lambda is our serverless compute service. Lambda has 3 execution models: synchronous, asynchronous, and stream-based. So in a synchronous model, you have commands using APIs like we just talked about. You're telling a service to go do something, go place this order, go do this thing. It's command-driven. Lambda is made to execute and returns a response once the code has finished executing. And this is what you think of when you think of testing applications, right? You create a test request, you send it to the API and make sure the response is correct, right? And then you do some end-to-end tests on the front end and you make sure each button and request that you make works properly. In an asynchronous model, you have events. Events are something that happened that trigger your Lambda function. And events within your application can occur and are observed by services, but are only trigger Lambda functions when those services are interested in that particular event. And so the response is returned upon invocation, and the processing continues in the background. So we talked about event-based and API-based, which are asynchronous and synchronous. And now let's go over stream quickly. So stream or pull-based architecture is where Lambda reads records from a data stream and invokes your function synchronously with an event that contains stream records. And across these 3 different execution models live a number of different services that can invoke your Lambda functions. Lambda functions are composed of 3 parts: the handler function, the event object, and the context object. The handler function is the function that's executed when the Lambda function is invoked. The event object is the JSON object that's filled with data that's sent to Lambda during function invocation. And then the context object contains methods that are available to interact with runtime information, such as the request ID or the log group. Many times when developers start building serverless applications, they start in the AWS console. You choose the services you want and connect them. And although this method is a really great way to learn, problems arise when you want to move your resources to different accounts, move it from one environment to another, or simply replicate what you've done in the console. Chances are you're not going to know exactly how you set up the resources in the first place and exactly which configurations you set. This can create unwanted variance in your test results. To solve this problem, use the AWS Serverless Application Model templates. A SAM template is a YAML file in your application that contains all of the serverless resources that need to be deployed. Upon deployment, the template is transformed to AWS Cloud Formation, which creates a change set describing the required infrastructure updates. Cloud Formation then applies the change set to the stack. Using SAM templates and practicing infrastructure as code ensures that all of the resources and configurations for your application are consistent between your environments, thus addressing the "it works on my machine" phenomenon. And we're going to return to SAM when we talk about best practices later, but I just wanted to introduce this here so you have that idea. You know what serverless applications are, so let's go over the challenges you face with testing them. Serverless applications live in the cloud and are composed of managed services. To test your code fully using managed services, you need to emulate the cloud environment on your local machine, unless you're testing in production, of course. However, this is usually not practical. There isn't a way to fully and accurately emulate the cloud. Secondly, using managed services for event-driven architecture means you must also account for external resources like queues, database tables, and event buses. With synchronous workloads, such as a traditional web service using APIs, you make a request and assert on the response. The test doesn't need to do anything special because the thread is blocked until the response returns. However, in the case of event-driven architectures, state changes are driven by events flowing from one resource to another. Your test must detect side effects in downstream components, and these might not be immediate. This means that the test must tolerate asynchronous behaviors, which can make for more complicated and slower running tests. And lastly, with serverless applications, you do much more integration testing, which alters the standard testing pyramid. The standard testing pyramid above on the left indicates that systems should have more unit tests than any other type of test, and then a medium number of integration tests, and then the least number of end-to-end tests. When you're testing serverless applications, this standard shifts to a hexagonal structure on the right because it's mostly made up of 2 or more AWS services talking to each other. So we just saw this new hexagonal structure. Now let's put them into practice. We're going to talk about 3 different types of tests: unit tests, integration tests, and end-to-end tests. Unit tests validate individual units of your code, independent from other components, and they check the smallest unit of functionality and should only have one reason to fail: that unit is not correctly implemented. Unit tests generally cover the smallest units of functionality, so typically one Lambda function, and the number of unit tests depend on the size of these Lambda functions. Next, we have integration tests, and the point of integration tests is to make sure that 2 components of your application work together properly. Integration tests are important in serverless applications because they rely heavily on integrations with different services. So we just saw this new testing pyramid and why it's so important to have integration tests in serverless applications. So I'm going to dig a little bit deeper here. So with integration tests, you want to programmatically verify the state of your infrastructure as a whole after it's been deployed. And running these sorts of tests can expose problems across whatever complex dependencies your infrastructure has. These dependencies aren't always obvious from looking at a single resource. Running these tests can give you visibility into these dependencies and verify that you haven't broken anything. These tests can also expose downstream failures in a way that unit testing can't. The changes you're making could have a wider scope than just the functional requirements in your environment. Integration testing can also be used to expose gaps in security, and verifying your changes after they've been deployed can help verify those changes. So, how is integration testing different on AWS, and specifically like using serverless applications? How is integration testing different? We know that there's more of them, but what else? The first thing that's different about deploying infrastructure on-prem versus AWS is that on-prem you get used to having stale and inconsistent environments. So if you're not already provisioning your infrastructure as code, you know the pain that's associated with having stale environment configurations. Infrastructure as code, so those SAM templates that we talked about before, solves all of those problems because you can deploy your changes programmatically and immediately across all of those environments. On-prem, there is no way to justify buying hardware. Provisioning of production-like hardware on-prem On-prem, there is no way to justify buying hardware. On-prem, there is no way to justify buying hardware. Provisioning of production-like hardware on-prem for a system that's not going to be handling a production workload. In fact, sometimes a single server is running every layer of your application, and sometimes it's running multiple applications. So you can't have a production-like system on-prem because of the financial impact. And when you're using infrastructure as code and deploying it to the cloud, you can provision a test environment just to run those integration tests and then destroy it when you don't need it anymore and you've only paid for the few minutes that those tests have run. The third and most important difference is the culture change that comes with moving into the cloud. On-prem, you've gotten really used to having functional silos for each part of the deployment process. So the IT team manages infrastructure, the application developer tosses artifacts over the fence to deploy on that infrastructure, the database team only does databases, the security team can only look at static reports from code analysis or running periodic pen tests, and no one on the technical side has any idea what anything costs because the hardware in the data center is already a sunk cost. The only thing that we did know is that there were never enough servers to do what we wanted in non-prod systems. And so then when issues occurred, it was always a struggle to determine who has the responsibility to determine a root cause and who has the authority to fix it. But when you're deploying things into the cloud using IAC, those silos are flattened and teams own everything that they build. The IT team can automate the heavy lifting of what they were doing before and focus more on strategic initiatives. Application developers can provision infrastructure on their own without having to wait for another team's availability. And you can migrate fully managed database services and focus on the business value of the data itself and how your application interacts with it. Security teams can now get full visibility into the entire system and implement guardrails and remediations to prevent breaches ahead of time. And what each implementation costs is transparent to the teams that have ownership over their cost optimization. So it's a paradigm shift for many customers, but it creates the autonomy and efficiency that allows your teams to use the skills that they already have to do more than they could before. But with that ownership comes a lot of responsibility to put processes like integration testing in place to guard against the kind of production issues that we're talking about. You can also configure test events and manually test two services directly from the Lambda console. Remember that when you test a Lambda function, you're not only testing the business logic, you must also mock its payload and call a function invoke. So there's over 200 event sources that can trigger Lambda functions. Each service has its own unique event format and contains data about the resource or request that's invoked, that has invoked the function. Okay, next is end-to-end tests. So End-to-end tests should test your user flows in production. And so you want to think about, what are your users doing in production? So you have your services in the back end that connects to your UI in the front end. And when you're testing serverless applications end-to-end, it's important to understand your user and data flows. So think about the most important business critical flows of your software and what should be tested end-to-end in your UI. From a business perspective, these should be the most valuable user and data flows that occur in your product. Another resource to utilize is data from your customers. So from your analytics platform, find the actions that your users are doing the most in production. End-to-end tests should be running in your build pipeline and act as blockers if one of them fails. They should also be updated as new features are added to your product. The number of end-to-end tests depend on the app complexity. Okay, let's dive a little bit deeper into the best practices of testing serverless applications. When you're testing integrations, the test must patiently wait for the message to appear. So generally, it sleeps for a configured length of time before waking up and asserting that the message exists. Now, the problem with this approach is that the test always sleeps for a set period of time. Regardless of how long the message takes to appear, for any given run, the test is always either slower than it needs to be or fails because it hasn't waited long enough. So rather than sleeping, a more effective approach is to pull the service until the message exists. So you configure the maximum time we're willing to wait for the message to appear and tolerate failing assertions during this interval. As soon as the message is detected and validated, the test is going to pass. So this means that our test always completes as soon as possible or times out if the threshold duration is exceeded. So let's say that every time an object gets put into an S3 bucket, that it should write something to a DynamoDB table, and there's a queue in between the services to handle traffic. In my test, I put something into the bucket and then pull my DynamoDB table for the message. So you're validating that this message made it to the final service. I don't care if it goes through the queue as long as it gets to the destination. You want to think of the end result here. So A happens and B should be the result. If for some reason your event is not being delivered to a target, you want to understand why. And the easiest way to do this, to debug this, is to add a dead letter queue to your rule and set your retry policy to 0. And what this means is whenever something fails, it's going to get put into this other place where you can see all of the information about that event. And you can look at, in your DLQ, you can look at the attributes of the event, and the attributes are going to contain an error of that entry, and that's going to show the error that you received when you tried to invoke the target. So this is another best practice, is to use dead letter queues to debug your event-driven applications. Another challenge when you're testing events is to make sure that your rule patterns are structured correctly so that the services are listening to events, come in and take action whenever it's needed. So one way you can test this is from the EventBridge console. So from the EventBridge console, when you create an event, you can test the event pattern to make sure that the sample event matches the event pattern. So in our coffee shop example, you want to think about this, like make sure that the pastry chef responds to requests for chocolate croissants and not for espressos. Instead of having the Lambda function sitting out there waiting to be invoked, a best practice is to use CloudFormation to deploy them as part of your pipeline, and you're going to use something that's called Safe Deploy with AWS SAM. So those Lambda functions are going to be in your code repository, right along with all of your code that's making your infrastructure changes, and you have the same Lambda actions as part of your pipeline to deploy or execute those Lambda functions, which are going to execute the tests and then go to production assuming everything is kosher and the tests pass. So you can also build the Lambda functions right into your stack. And I just want to talk about safe deploys for 1 second because they're a really important part of testing. So safe deploys allow you to manage your test stack. So you have your pre-traffic hook and your post-traffic hook. So before traffic shifting starts, code deploy invokes the pre-traffic hook Lambda function. This Lambda function must call back to code deploy and indicate success or failure. If the function fails, it aborts and reports a failure back to AWS Cloud Formation. And if the function succeeds, code deploy proceeds to traffic shifting. After traffic shifting completes, code deploy invokes the post-traffic hook Lambda function, and this is similar to the pre-traffic hook where the function must call back to code deploy to report a success or failure. Using post-traffic hooks to run integration tests or other validation actions is a best practice. You can also set deployment preference types, either canary or linear or all at once. And effectively, you could have the application Lambda function, a pre-traffic test Lambda function, and a post-traffic test Lambda function. And if any of them fail, the entire stack rolls back. So these three types of Lambda functions can point to they can be separate Lambda functions, or they can point to the same Lambda function, but it's just at different times in the deployment process. And so by adding this auto-publish alias property, AWS SAM detects when new code is being deployed based on changes to the Lambda function's Amazon S3 URI. It creates and publishes an updated version of that function with the latest code, and then creates an alias with a name that you provide. It also points to the updated version of the Lambda function, and function invocations should use the alias qualifier to take advantage of this. So safe deploys are really a best practice when you're testing with Lambda. Another thing that you can add to this are alarms, and we already talked about hooks, but alarms are CloudWatch alarms that are triggered by any errors raised by the deployment. They automatically roll back your deployment. So an example of this is if the updated code you're deploying is creating errors within the application. Another example is if you have a Lambda, or if you have a Lambda function or custom CloudWatch metrics that you have specified that have breached the alarm threshold. And then we talked about pre-traffic and post-traffic hooks. So you have pre-traffic and post-traffic test functions that run sanity checks before traffic shifting starts to the new version and after traffic shifting completes. So the next best practice is to deploy the Lambda functions along with a step function state machine that's going to define how the Lambda functions are going to be run and define a more conditional workflow that you can use to create a more dynamic test run. So you use a code pipeline action to invoke that step function state machine, and as you do that, the start state will go, in this case, run in parallel, and they'll run tests against the test environment, and then they'll consolidate their output and return that back to the pipeline, and then onto production if everything is okay. Some advantages are that we have consolidated test results that can be propagated to dashboards or email reports. You can use all of those service integrations with step functions to configure notifications or remediation actions depending on how severe those issues are. Step functions also allow you to orchestrate the test and not just in parallel or in series. You can have conditional flows, like if a test fails, I want to run these other tests, or maybe I want to run the same state machine against a development environment and my integration test environment, and maybe even against production, and only run a subset of my tests against each environment so that it can speed up my build time. You can also configure error handling and retries as well as a part of step functions. And if you create the pipeline itself within CloudFormation with or without the CDK, it's a pattern that can be used as a starting point for new projects and shared across teams, so you can start propagating these best practices of running integration tests as part of your infrastructure deployments into the future. Another best practice is to narrowly scope your tests. So when you're testing asynchronous events, you have some side effects, and these side effects can be tricky. So not only must you monitor different parts of your system, you also need to know when to stop waiting and abort the tests. So we talked about polling earlier. So when there's multiple asynchronous steps, this delays your test, and it adds to your longer running test times. So there's two approaches. So we talked about polling. Another approach is to narrowly scope your tests. So you're going to want to write narrowly scoped tests for each asynchronous step. And so this limits the possible causes of asynchronous test failure that you need to investigate. And so with fewer asynchronous steps, these tests are going to run quicker, and it's going to be easier to estimate how long to wait before timing out. Another way to debug serverless apps is by using the AWS SAM CLI for debugging, and this is another best practice. So with a traditional workload designed to run on a server or in containers, a developer will typically run the entire application on their local machine. And as they make changes, they get rapid feedback by deploying to a local runtime environment, invoking the application, and debugging any issues. When you move to a serverless architecture, you rely heavily on managed services in the cloud like Lambda, API Gateway, and S3. AWS becomes your runtime environment, meaning that at some point you need to deploy your changes to a remote cloud environment. You need to invoke resources like Lambda functions and inspect services like CloudWatch logs to debug your issues. And if you have to do this for every code change, your development velocity can drop significantly. To avoid this issue, you can source more or less of your development feedback from your local machine so you can verify your changes without deploying them. With the AWS SAM command line interface, you can locally test and debug your serverless applications before uploading your application to the AWS Cloud. Using the SAM local invoke command, you can verify whether your application is behaving as expected, debug what's wrong, and fix any issues before going through the steps of packaging and deploying your application. When you locally invoke a Lambda function in debug mode with the AWS SAM CLI, you can then attach a debugger to it. With the debugger, you can step through your code line by line, see the values of various variables, and fix issues the same way you would for any other application. Another best practice is to use infrastructure as code for consistency between environments. Infrastructure as code helps eliminate configuration drift. Let's say you get paged one night because there's an incident for your mobile application. You look at the logs and identify the problem. In order to fix it, you need to update a specific configuration in production. So you go and you make the change in production and you go back to sleep. Although you fixed the issue, you've just created an even bigger divide between your staging and production environments because you did not make the same change in your staging environment. Many times, staging environments are not the same as production because of changes made during incident management. This is called configuration drift. When you use infrastructure as code, rather than having that shift in environments, you have one central authority that is this SAM template, and then you push the infrastructure changes through. And here's what an example SAM template looks like. It's written in YAML, and you can see that there's a few resources being created here. You have a Lambda function, a DynamoDB table, and an API. So I created the Lambda function out of the corresponding IAM role that lets the Lambda function talk to DynamoDB. And there's a lot of options when it comes to policies that you can add to your services, and all of these are in the AWS documentation. So you can add whichever policies that you need. So we're creating an API from API Gateway. So your event source for your Lambda function here is this HTTP API, and you can configure these templates to add any AWS resources and create your application, and you have a lot of flexibility to build what you want. So with these 20 or so lines of code, this on the left becomes this on the right. So you have the Lambda function that's triggered by API Gateway, then you have the DynamoDB table that stores all of the data, and what's already created for you is the permission for API Gateway to invoke the Lambda function. And so this happens automatically for you in SAM when you set API Gateway as the event source for the Lambda function. And then you added the policy saying that you can only read from the table, and that is completely customizable. So this is all, these 20 lines of code can be used to deploy in different environments, ensuring consistency. So what did we learn today? We learned about serverless and event-driven architecture. We learned about the challenges with testing serverless applications. We learned about this shift in your traditional testing pyramid with an emphasis on integration tests, and we also learned about the best practices for testing serverless applications. We have a ton of content and learning opportunities on serverlessland.com that my team and I are constantly updating, so be sure to visit us if you haven't already. Thank you so much for listening today. This is my Twitter and my email address in case you all have questions. Hope you all have a wonderful day.